Good afternoon. This is David Eastwood, Geotech Engineering and Testing. How are you all doing today? Um, Today we're going to be talking about geotechnical consideration and design and construction of bridges. Welcome to 2026. We got about 180 people RSVP'd, and most of the people are civil engineers, structural engineers. A lot of the people from like cities and the counties. 180 people. If you need to reach me, here's my contact information. My email is d@geotecheng.com. My number is 713-699-4000. This is going to be on YouTube channel, so you can go watch it, and you're going to get continuing education certificate on this thing, a PDH. Geotech Engineering and Testing has been around about 40 years in Houston. We work all over Texas, Louisiana, New Mexico, and Oklahoma. We got about 60, 65 people who do geotechnical, environmental materials, and geoforensic engineering, a lot of failure stuff. And so if you have any questions, you can ask the questions in the chat or Q&A so I can respond. So let's see if I have anything in there now. Yeah, I can hear you too. So, okay, that's fine. I can see your screen. I can hear you loud and clear. Okay, that's good. We're good. Okay, we're going to be talking about bridges. Houston Ship Channel. It's one of the biggest bridges in Texas. Beautiful structure that's going in. Harris County Toll Authority, they're doing a great job trying to get this thing going. Hopefully it'll be finished soon. There's some pictures of it. We got bridges all over Texas, and you can see these overpasses and flyovers everywhere. Got smaller bridges, got big bridges. A lot of these bridges are supported on drill piers, or they're supported on pre-stressed concrete piles. It's a small bridge for subdivision, overpasses. It's a bridge out there in the Woodlands, Texas. See more bridges. The Chimney Rock Bridge, South Rice Bridge. These are Harris County flood control projects. This is a Hillcroft Bridge, and you can see it and notice the concrete paving out here on the slopes for erosion protection, or slope paving actually, so we call it. Pedestrian bridges, we've got a lot of that going on. These pedestrian bridges are supported either on drill piers or spread footings. These are the big bridges. This one here, State Highway 99. Here's the rig here. We're doing a boring out there for it. They're gonna whiten it. Bridge failure. Yeah, if you don't design them properly, they're gonna fail. It's another one. It's another one. Timber bridges, they kind of fail here and there. Pittsburgh Bridge failure, that happened in 2022. That was a real big deal. It's all snow and everything, and the whole bridge kind of failed. Yeah. It said the bridge failed due to inadequate load capacity. So I don't know how they designed it, but it didn't have the capacity for the load. Minneapolis Bridge, that was the bad one, 2007. If anybody remembers that one failed bad. This one had a design problem, apparently. TxDOT bridge failure, I-10 next to, on I-10 and San Jacinto River. I don't know, I remember that one. A barge came in and hit these columns here. All right, I don't know what happened. We had a technical problem. We're back. This is the San Jacinto River Bridge, and in November of 2019, and the barge hit the columns. Everything collapsed, and you can see the pictures here. Do the sonar in here. You can see the columns here are busted. Here's another column kind of busted. All right, TxDOT got a new design manual that you have to go with AASHTO LRFD design procedure for bridges and the foundation. Load and resistance factor design, LRFD, applies to statistical factors to loads and materials to ensure uniform level of safety and reliability. Okay, and they got boring locations, typically 300 foot apart. But if you got bents at 100-foot spacing, you need to put borings out there every 100-foot spacing. So essentially, doubled and tripled the geotechnical requirements for bridges. So we're doing borings at roughly every 100-foot spacing. Boring should be located 100 foot or less from anticipated the center of each bent substructure or abutment. So essentially at each bent, you need to get a boring out there. Boring should be located 50 feet or less from anticipated center of any mono shafts on the bridge. Drilling and sampling, these are our rigs here, some of our rigs. These are truck mounted rigs, and we've got portable rigs, we've got truck mounted rig here. Traffic control that you need on some projects. Got to be done according to Texas Manual, Uniform Traffic Control. So we go out there and do borings. Out there, small bridges, one at each end usually. You got to do slope stability as well right here. So drilling, sometimes use portable rig at the toe for the slope stability analysis at the abutments because the soils at the toe may be different than the ones at the top. There's going to be a lot more sand and silt in here because of the siltation. So here's the portable rig system. It goes about 20 feet deep. These are some of the bridges we're trying to widen or replace. Doing borings out there at the abutment near area. This is a pedestrian bridge that we're going to do borings for. These are buggy rigs that we use for bridge if you have access problems. Here's a tow road project. We're doing borings for it. See State Highway 99 out there between I-10 and 1093, lane widening, putting bridges, widening the bridges, pour the concrete first. We got overlays sometimes on some of these roadways. You got concrete underneath it, so you got asphalt over concrete. You got to cover it up after you do the borings, and of course you can do water level measurements. After you finish the borings, you're gonna have to grout them. You mix a mixture of the bentonite and water and cement. You mix them together. You get a hose. You pump it from the bottom of the hole up to grout the holes when you finish drilling. You check with a probe to make sure your grout is good so that it doesn't fall into the hole. It'll be nice and hard. On projects that are really wet, we use our buggy rigs. And of course, if you got bents out there in the near shore areas or in the river or bayous and stuff like that. You gotta get a barge and do the borings. Here's a kind of ship channel area, doing borings off the barge. You got a moon pool here, and do the borings right there. Here's the rod. So in areas that are wooded, of course, to get to the location of the bridge, you may have to do some clearing. So gotta have to dozer to go clean it up. You have an access. Most of the sampling is done with Shelby tube samplers. These are 3-inch diameter tubes. You hydraulically push them into the soil, and this is how you get your soil sample. We look for root fibers. That tells us the depth of the active zone. That's the zone at which soils experiences shrink swell problems. Roots extend into the soil and where there's oxygen and water. When there's no oxygen and water, roots stop. That's important for the design of your piles or drill piers. TxDOT is now requiring standard penetration tests at 5-foot intervals on all the projects. They don't require Texas cone penetration testing anymore. So we run a standard penetration test. It's a 140-pound hammer, drop 30 inches, like that. You drive them to the ground 18 inches, 6 and 6 and 6, 6. It's a 140-pound hammer, drop 30 inches. That's the SPT results. That's what we get on all the TxDOT projects now. No more TCPs, no more Texas cone penetrometer. These are the SPT stuff. So if your blow counts between 0 to 4, it's very loose material. Loose 5 to 10, medium dense 11 to 30, dense 31 to 50, very dense over 50. So if I've got a bridge and I've got sand, I want to drive it into the dense material, hopefully, or very dense to get high end bearing, skin friction. Texas cone penetrometer. TxDOT used to use that. It was good in rock, but not in soils. It's a 3-inch diameter cone. There it is. You drive it in 24 inches. That's the rig. You measure 24 inches right there. It's a 170-pound hammer, drop 24 inches. You drive it in 12 inches for seating, and then 6-inch and 6-inch, and measure the blow counts. The diameter is 3 inches. So when you get the blow counts, for example, if the blow counts is 0 to 8, and for soils, if this clay is very soft, sand is very loose. 8 to 20 is soft clays and loose sand. 20 to 40, you got stiff soils, slightly compact sand. 40 to 80, very stiff soils, compact sand. 80 to 5 over 100 blows, hard clays, dense sand. 0 to 5-inch over 100 is very hard soil and very dense. Now, if you drive them into rock, if you have a blow counts 0 to 2-inch over 100 blows, you got sandstone, you got chert, granite, real hard rock. If it's 1 to 5 over 100, you're going to have siltstone, shale, iron deposits, limestone. 4 to 6 over 100 blows, you can have gypsum, calcite. So you're going to run into stuff like this if you're in San Antonio, Dallas, Austin. We don't run into it in Houston. TxDOT is now requires rock coring. If you hit rock, you don't do TCP anymore. You got to do coring and run unconfined compression on the rock cores or RDQs. So these are the cores. You log the soils as you drill. Got the ants. You put it in plastic bags. And you put it in foil. Keep the moisture constant. And here's you put them in the plastic bags. You got to test it right away, otherwise you lose moisture. You got to get the water level measurements at the embankments, abutments area for slope stability analysis. You put piezometers in there. These are PVC pipes that are perforated. You put it in the hole. They're coming in 2-inch or 3-inch diameter PVC pipes. You put it at the abutments to know where the water level is for your slope stability analysis. You put it all the way down there. You backfill it around it with bentonite. You got bentonite balls you put in there, and then the top area you make grouted with cement grout. Of course, around it, in the screen area, you put sand to allow the water to flow. And then, bentonite balls above the sand. That's the piezometer. You put a steel cap on it, or you can, let it stick out of the ground like this. You get a tape measure. You go measure the water levels. So it's a typical Harris County flood control design here for piezometer. You got the screen. You got sand around it. Above it, you got a couple of feet of bentonite pallets. And above that, you do grout it with cement and bentonite grout all the way to the top, and sticks out above the ground. You can cut it right over here and put a steel plate on it if you're in the roadway, for example. Regular water table, like in Houston, could be 20 feet, 25 feet. In Dallas, San Antonio, Austin, can be 20 to 40 feet, 50 feet, Same with Austin and San Antonio. The groundwater is going to be deeper over there because of the climatic condition. There's less rainfall, so therefore the groundwater is going to be deeper. The way you measure water levels, you put a tape. You get a tape with a weight at the end of it. You throw it in the hole. When it goes plumb, you measure the water level. We do a lot of our geotechnical work based on City Houston geotechnical guidelines, a design manual, which refers to TxDOT design manual for bridges. Same with Harris County design manual that uses TxDOT for bridge design. If there is TxDOT funding, of course, Harris County Flood Control, they got their guidelines for geotechnical work. And of course, TxDOT came up with April 2024 with their new bridge division LRFD design geotechnical manual. Number of borings, we talked about the bridges. With roads, we typically do one boring every 500 foot. For MSC walls, we do one boring every 200 foot apart, twice the height of the wall. With ditches, we could do one boring every 500 foot, twice the height of the ditch. Detention ponds, depending on the acreage, we start with 3 to 5 borings for the first 5 acres, and then one boring every 5 acres. For signs and structures, we do one boring, typically about 40 feet, sometimes 60 feet if the sign is very tall. Sound walls, we do 30-foot borings with drill shafts you got to put in there. Others, depends on the structure. For small bridges, we do go 80 feet below the bottom of the channel basin. So if your channel is about 25 foot deep, we do borings 150 feet, under 105 feet for small bridges. For pedestrian bridges, we go at least 40 feet below the bottom channel. So if your channel is 20 feet, we go 60 feet deep. Large bridges depends on the loading. We're doing a lot of bridges, that 120 foot deep borings, 130 foot borings, just depends on the loading. Okay. Let's see. Okay. Laboratory testing, a couple of the lab testing that we do, of course, we do liquid limit tests, trying to see the soil, Heidelberg limit for the soils. And so we take a soil, you mix it up with water here. And when it becomes liquid, you put it in this cup, cut a groove through it, turn this handle 20, 30 times. When the groove comes together, you get a sample of it. You get put it in a scale, get the wet weight of the soil that's wet and liquid. Then you dry it up in the oven and you put it back there, and then you get the dry weight of it. So we find out how much water is required in the soil for it to behave liquid. Plastic limit test, we run the test, put the soil 1/8 of an inch in diameter. You roll it up, you get the wet weight of it, trying to find out how much water should be in the soil to behave semi-plastic. You dry it up in the oven. And once we get a dry weight of it, and so we find out how much water should be in the soil for it to behave semi-plastic. The difference between liquid and plastic limit is plasticity index. If your PI is less than 20, you got low soil potential. Between 20 and 30, you got moderately expansive soils. 30 to 40, you got highly expansive soils. Above 40 is very high. That's a slide that was out of whack here. That's a plastic limit test. The other test we do in the lab, hand penetrometer and a torr vane. In a hand penetrometer test, we take the sample, we push this into it. You can read what kind of a strength you have. You do this in the field as well. Torr vane test. You put this thing, torr vane, at the end of the sample, ensure it in torsion. You can read what kind of a strength it has. Unconfined compression test. You put your soil sample in here. You got the proving ring, deflection. You shear it to see how much load it carries. All this stuff goes for design of your drill shafts and your piling, and also your slope stability analysis at the abutments. Unconsolidated, undrained, it's better than the unconfined compression test. You put the soil in this device in a cell, and of course you put it in a plastic film, and you put a lateral load on it as well, so that to model the in situ loading condition, three-dimensional loading, usually get a higher strength. But with the lateral load on it, it's a total stress test. You shear the soil, in unconsolidated, undrained test. For your slope stability analysis, you do triaxial testing. You put the soil sample in this cell here. You put three-dimensional loading on it to model the in situ at the depth that you want. Let's say it was 20 feet deep. You get 120 times 20 deep, and that's your cell pressure. And you multiply that level. Let's say this is 10 psi, then 20 psi, and 30 psi confining pressure, and you run the test, and you develop Moore's envelope. The triaxial testing, you shear it. These are the stress strain curves. You got total stress and effective stress. You take out the pore pressures, you get to the effective stress. C and phi angle for effective stress. C and phi angle for total stress. Again, you use this stuff for slope stability analysis. If you have sandy soils, it's hard to do triaxial test on it. So you do direct shear test. You put the soil in this little area like this cell. You put the sandy soil in there. You put this cap on it, shear it in torsion in a horizontal plane. And that test, you put the confining pressure on it, depending on the depth of the sample, like a 10 psi, 20 psi, and 30 psi. And you shear it horizontally, and you get the stress strain curves, and you get the effective stress envelope from it. Do gradation tests. That's important, especially for scour analysis. You want to know what kind of a gradation your soils have. You put the soil into sieves and shake them. You combine it with the hydrometer test, and you get gradation curve in here. In this case, you got fat clay, and you can see 96% passing number 200 sieve. The way hydrometers run is basically a soil specimen dispersed in water. In dispersed state, the soil particles settle individually in the water. It assumes that the soil particles are spheres, and the velocity of the particles can be given by Stokes laws. It's kind of hydrometer soil in there. You kind of put it in the water, and you mix it in, and then you throw it in there, and you put a hydrometer in there, and you go through calculations, and from that you can find the grain size. This case here, grain size here. You can run it up to 200 sieve with regular sieves. After that, you got to use hydrometer. Here you got 66% passing number 200 sieve. It's a sandy clay material. Engineering analysis, the soil types that we have in Texas, we have a lot of clays. It's a clay site. It's got sandy soils. You got that, sandy soils. We got it like in Galveston. Sandy sites. Silt. We got a lot of silt all over the place. You got it all over Texas. We got silt. We also have gravels in parts, especially you go through some of these channels and bayous. At about 30, 40 feet, you may hit gravel. Measure the size of it. You run into siltstone or sandstones, especially in Houston area, that you're going to run into near the channels. That's what they look like. So we have clays. You go deeper, you got orange clay, you got white clay. Below that, you got weathered rock. Below that, you got rock. Again, now TxDOT is requiring to core the rock and test it. We don't do TCP in it. Fill, you can build your embankments on fill. All your abutments are on fill. Your approaches and stuff, they're on fill. All these soils should be compacted to 95% standard proctor density. Typically, if you got a tall embankment, we tell them to compact 100% standard proctor density. Or TxDOT, the same concept. They got their own compaction, which is similar to ASTM. We just got to make sure your fill is got free of organics, and you can compact and make sure you have no, deleterious materials in it. Now, if you use fat clay for your embankments, that may be a problem with shrink swell problems when slope stability. So you got to look at the material that you're going to use for the embankment, make sure they're not fat clays. In terms of soils around the Houston, we can start from the woodlands area where your soils are sandy, low PI soils to Roman forest here. You got sandy soils. You go to Kingwood, you got fat clays. And you get next to Lake Houston, you got all sandy. You go to Dayton, Mobile View, Baytown, Anahuac, you got all fat clays. LaPorte, Pasadena, League City, Missouri City, City of Sugar Land, New Territory, Pecan Grove, Rosenberg, all these places, you got really fat clays. You go to Katy areas, it becomes sandy. That Brookshire area, Waller, you got very sandy soils. Fairfield, Bridgeland, sandy soils. Tomball, Party, sandy soils. Party, fat clays. Magnolia, you got sandy clays and some sand out there. So just depending. And if you look at the whole Texas, you go to Dallas, San Antonio, and Austin, those areas, you're going to run into rock or bridge stuff. So you're going to have to core the rock per the new TxDOT standards. You cannot run TCP on it. Although I really like TCP in rock, but I don't like it in soils. You're going to run into soils that are really fat clays. They dry up during the summertime and they develop shrinkage crack. That becomes a problem for your abutments. If you got fat clay in it and causes slope stability problems. These shrinkage cracks get filled up with debris over time. And then we get a big rain, the soil wants to heave up, close this thing. It cannot because it's got stuff in it. And the cracks, so basically got 45-degree angle. It's called slicking sides. So if you're doing drill piers, some of these drill piers can fail. The bales and stuff like that because of presence of slicking sides. If you're doing any trenching, side of the trench may fail because of the slicking sides. Looking at the Texas soils, we've got a lot of fat clays. Dallas, San Antonio, and Austin. The Midland Odessa area, you got caliche and sandy soils and silt. Don't have much of that anything problem, So we got all the major metropolitan areas is where we have a lot of fat clays. Texas soils are variable. So every time you do a bridge, on and off bridge type project for TxDOT or rural, you're gonna have to get borings out there and make sure you know what the soils are. These are the soils that expand up to 1,500% throughout the U.S. You can see them all over the place. So we got a lot of expansive soils throughout the U.S. This is based on U.S. Corps of Engineers. So when they did the land plan for Texas, they put Dallas, Fort Worth, Austin, San Antonio, and Houston in the area where you got a lot of expansive soils. Beaumont, Corpus Christi, Brownsville, all these areas got expansive soils. And you can see the expansive soils in Texas and Louisiana, the red stuff. North of Buffalo Bayou, your soils become sandy. South of Buffalo Bayou, the soils are fat clay. New TxDOT boring log. Again, TxDOT doesn't like to use TCP anymore. So we're doing SPT every 5 feet on all their borings. This is a project we just finished for Fort Wayne County Toll Road. And you can see, the fat clay here near the surface. We do TCP we do any SPT every 5 feet, and right below it, we go get a Shelby tube sample so that we can run unconfined compression, hand penetrometer, UU tests. But if y'all all sand, we just go out there and do SPT every 5 feet all the way to the bottom of the hole. Here's where we hit the water about 20 feet or so. And these are the tests in the clays, the strengths in the clays. So that's all the new logs going to look like for TxDOT projects. Old wind core, that's what they look like, where you had the TCP results in here, 40 and 30, 40 for 6-inch, 30. So that was a 70. Blow counts, it's a fat clay, stiff. And you have the pan penetrometer, 1.5 TSF, the PIs and the unit weight. That's the old stuff that we use. We just finished a contract that we started with the TCP. We'll finish it with the TCP. But all the new projects that we do, we have to use the new TxDOT guidelines. If there's TxDOT funding available, or the client says use TxDOT standard. If they don't, we just go out and do our regular borings, which we just do, sampling every 5 feet, and we get Shelby tubing clays and do SPT in sands. I don't think it's very productive to do SPT in clays, but that's what the new TxDOT is talking about. Again, I don't understand why you need to run SPT in clays. We plot the data. This is the moisture content versus depth, undrained shear strength of the soils versus depth, dry weight. So this is the total unit weight here. You see the high moisture area, you got the low strength. The low moisture area, you got high strength. So we plot that to come up with the parameters for design of your piles or drill piers or slope stability for your detention pond. So if you're doing a TxDOT project, and I'm talking about TxDOT in Harris County, City of Houston, you're going to have the bridge, roadway, a detention pond. That's kind of typical, that some of these projects go. If you're doing like a roadway project or a bridge, you can line up all the borings out there right next to each other. You got a sand layer here. Got clay and sand and clay. Pile foundations, depending on the projects, these could be steel pipe piles on big projects. You drive them with a Delmike hammer. TxDOT like to use pre-stressed concrete piles on a lot of their projects. This is the TxDOT 288 at Sims Bayou. The bridge has got lots of pre-stressed concrete piles. They're great. They got big surface area, big end bearing, great foundation system. You drive them with a hammer. This is a diesel hammer. You drive them into the ground. That's a Delmike hammer there. drive them in. Here's the bridge abutment. You drive the piles in. Now, if you're in an urban area, that may cause a problem. When you drive piles, it causes a lot of vibration of the nearby structures. So you got to make sure you check some of those structures before you go out there and start driving piles, because there could be a litigation out there that you have damaged the foundations for some of these structures. So before you drop piles in an area that's got a lot of buildings around it, you got to go take pictures and observe all these buildings and structures for signs of distress and document it before you actually do it. That's why, in urban areas, we use drill piers, so we don't have to worry about that problem. Here we're driving piles here. These are pre-stressed concrete piles. This guy here, engineer, was Aggie, so he put him at an angle. No, I'm just kidding. This take care of lateral loading and putting like that. Timber piles on small, like a pedestrian bridge. You could be driving, timber piles. They're round or square, 10-inch square piles. You just drop them in with a drop hammer type stuff. Here's another project. We're using a hammer to drop the timber piles. You cut the top of them. We don't drive them to crack them up, so make sure they're not cracked. Soil structure interaction, new design procedures. Since we don't use TCP anymore for pile design, I personally use A.P.I, American Petroleum Institute design for pile design. I've used them for 50 years. They're updated all the time, and it's a pretty good design for design of the pile foundations. For clays, skin friction is alpha times C. C is the shear strength, and alpha you calculate like this based on C over P ratio and effective overburden pressure. For end bearing, of course, is 9C, 9 times the shear strength. For sands, F times KP, PO, tangent delta, and that's a friction angle between the soil and the pile. For end bearing is P naught, which is the overburden burden times N sub Q. And so limiting values for cohesive soils, for steel piles, you use F max 1.0, for timbers 1.42 KSF, the limiting value for skin friction. A.P.I.'s got values for, let's say, loose sands. You got a friction angle of 20 degrees, limiting skin friction of 1.4, NCQ of 12, and limiting unit end bearing of 60 KSF. So it's got a table with limiting value and limiting skin friction. There are other methods out there, depending who one you want to use, but I use A.P.I. Old textile procedure, use axle capacity with Texas TCP, and now we got to use standard penetration test. Texas cone, they got a really good stuff here as it relates to rock. But this is for soil, of course. For soils, the value is less than 100 blows per foot. Texas cone penetrometer value, and from that, you're going to get allowable skin friction. If your soils is sand, clay, or fat clay, or other, 40 here, if you got, fat clay, you come here and you got skin friction of factor safety of 2 or 0.8 TCF, tons per square foot. If you use drill piers, you take that value and multiply for 0.7 for skin friction due to sample disturbance. So if you got a skin friction of 1.0 for piles, for drill piers is 0.7. And here's for TCP values, softer than 100 blows per foot. That's Texas cone, and this is a end bearing. So if you got a 50 blow counts and you got SC or CL type, or let's say you got CH, 50 at CH is 2.5 TSF, factor of safety of 2. So what I use on my projects, I use a factor of safety of 2 for piles, for both skin friction and end bearing. For drill piers, I use a factor of safety of 3 for end bearing and 2 for skin friction. Axle pile capacity, 1 capacity end bearing for piles of less than 24 inches is neglected due to a small area by TxDOT. So they don't count on the end bearing. Point bearings is considered for all drill footings. So if you use the pile foundation, if you've got a 6-inch square pile in here, you can have a maximum length of 85 feet. At the abutment, you can carry up to about 75 tons, and footings 125 tons. These are limiting values that specified by TxDOT. So if you got piles, you drive them to the ground, you got to disregard the top 5 feet in non-water crossing. Typically, I disregard top 10 feet, especially if you had expansive soils for drill piers, and 5 feet for the piles. You discard top 10 feet in the stream crossings, and you disregard all the piles in the abutments. So like here, you got a pile in a drill piers here. So in this case, you go out and I disregard top 10 feet skin friction, or 5 feet. You know, the TxDOT says 5 feet. So if you're out here in water crossing, if this is a drill pier or piling, I'm going to disregard the skin friction all the way from here to the bottom here. And I'm in the water, I disregard top 10 feet. Like here, I disregard really 10 feet. It's drill shafts in the water, to disregard top 10 feet here for skin friction values. Look at these other bridges here. You can see I would disregard all the skin friction from here to here. In the abutments, I'll disregard all the skin friction from here to here. All in the abutments, I disregard it. Here's another bridge here. I'll disregard the skin friction from here to the water area, all the way from here to the water area. This is a typical TCP. You drive them in there. You can see the TCP for skin friction. Okay, that's unit frictional resistance. And here's the end bearing that you can get it from WinCore program. So that's cumulative friction. So here's a capacity without end bearing, the red one. If you want to add the end bearing, here's the capacity. So, you know, foundation capacity of 60 tons at elevation plus 275, or roughly about, 30 feet deep. So this is without end bearing, and this is with point bearing. So you get higher capacity at shallower depth when you consider the end bearing. Here's the other capacity curves. You can see the depth versus capacity, basically calculated based on the API. And these are 12-inch square precast concrete piles. Goes all the way down about 60 feet. You got tension capacity and compression capacity. These are deeper piles. Go all the way down to 350 feet. It's ultimate capacity, factor of safety of 1. You got clay, sand and silt, clay, sand, silt, silty clay. And so clay, sand, and the clay. You can come over here, and when you hit a sand layer, you get a bump here. You come down here, you get another bump when you hit a sand layer. Like that, same here. That's a recommended capacity based on a factor of 2.0, and this is the capacity based on factor of safety of 1.0. There's no factor of safety, it's ultimate value. And these are tension capacities that you don't count on the end bearing. So you can see the end, of course, tension capacities are lower. This is based on factor of safety, the factor of safety of 1. That's based on factor of safety of 2 for tension. On the smaller projects, we may give E and F factors. F is allowable unit pile resistance, kip per foot, a pile diameter. So that's the F value. And this is the end bearing E. The way you calculate the capacity is for compression is PF, which is parameter times the F value plus area times E value. So if you got a pile that's 18 inches in diameter, your P parameter is 4.7 feet, area is 1.77, Q is, if you assume that's 30 feet, you can see your F value of about 6 point something, 6.14, and 4.5 at 30 feet is your end bearing. So your compression capacity is 36.9. Okay, these are allowable. They got a factor of safety of 2 in them. So that's for a kind of a pile foundation. For tension, you get that value multiplied by 0.7 for the skin friction, 0.7 PF. If it's all clay, you don't need a 0.7. Just PF would be your uplift capacity. Here's another one driven pile. You can come over here, end bearing. You got a sand layer in here. Here's your skin friction, F value versus depth. And you got Q, PF plus AE, the same thing. You go through it. Your QC is 22.4 kips. This is allowable. We got a factor of safety of 2. Your uplift is 12.2 kips uplift. For lateral loaded piles, you use PY curves. So when you got a bridge abutment out there or a bridge bent, you're going to analyze it for load settlement. You got to use TZ curves. For lateral movement, use PY curves. For torsional movement, use M theta curves or T theta curves, depending on what they call it. Here are the stuff from L-Pile that you're going to get. Soil parameters, for depth range, 0 to 2 feet. You got soil modulus of 80. A PCI, E50, that's a strain at 50% of the shear. Gives you the strain. Effective unit weight. Undrained shear strength of 600 PSF. If you're in sand, you got a soil modulus of 20. We don't have to about E50, but you got unit weight of 70. That's submerged unit weight. And a phi of 30 degrees. For load settlement calculations, if you have a pile foundations for a bed, for example, you use TZ curves. You get the piles, you break them up in segments. For the pile to mobilize its end bearing, you're going to have a certain amount of movement. That's described in the TZ curve manual. So if you move, your end bearing, your end bearing goes higher, and of course, if you move a lot, you get to a plateau. Same with skin friction. You got to move very little depending on soil, sand, or clay. You mobilize F over F max. So you go through the program, TZ curve program, and you can do a load test and you get a load settlement, and you can do a TZ curve and get your load settlements. On some of the projects, especially in the abutment area, we need to worry about negative skin friction. So you could be driving your piles. You're going to get into negative skin friction when soft soils surround the pile, around the pile settles and causes downward movement of the soils against the pile skin friction. So let's say you got natural soils, you go out there and build a 30-foot high embankment on top of it. And if that soil settles more than 2 inches, You can have negative skin friction on your foundation. You're going to have at least 2 inches of movement before you mobilize negative skin friction. For negative skin friction to occur, you can have, cohesive soils over sandy soil deposit. You can have fill that's placed over compressible cohesive soils. You can lower the groundwater, changing the effective stress on the soil and cause basically loading on the piles. For negative skin friction to occur, portion of the pile must be fixed against a vertical movement. So if your pile is in, say, let's say, is in tipped in sand, and you got compressive soils above it, as those soils start compressing and settling, it pushes on the pile and put more load on it. I use usually the beta method to calculate the down drag or negative skin friction. Skin friction on negative skin friction is equal to beta times phi times your static stress. Beta for clays is 0.2 to 0.25. For silts is 0.25 to 0.35. For sands is 0.35 to 0.5. The actual negative skin friction is F.ASCE is equal to skin friction times pile diameter times H. That's F value. So, which H is, of course, layer thickness. This delta type, or whatever we call it, is effective stress. And then F.S is a negative skin friction. F.S negative load in pounds. Group effects. When you put the piles close to each other, they're going to lose the load carrying capacity. This is from DM7 that says if you put the piles 3 diameters apart, although TxDOT allows it, TxDOT says you can put piles within 3 diameters and there's no loss in load carrying capacity. But this one here says for put the piles or drill piers within 3 diameters of each other for a 48 diameter pile diameters, 48 inch. No, that's L is 48 foot pile diameters, 3x3 group or 9x9 group. That's L is 48. I guess that's the length of it. So you can see you got efficiency of 0.7, or you can have 0.8 or point. So we talked about reduction in capacity of the pile. Now, if you got piles real close to each other, you go through this kind of a calculation of the group action to see the group capacity cannot exceed this block failure. So if you got the length of the block here and the width of it, you can calculate like a rectangular type system and calculate the skin friction around it and end bearing. And cumulative number of your piles capacities cannot exceed this. So this is going to make sure the lower limits, but it cannot be the higher limit. If you can use the efficiency factor here, you can use this for your actual total capacity, but it cannot exceed this, what we have in here as a block group. Pile driving, you drive the piles, you can use a steam hammer or you can use a diesel hammer to drive the piles. This is Galveston, we're driving piles there. TxDOT's got a spec for pile driving. TxDOT spec 404, refusal 0.1 inch, penetration per blows, or 120 blows per foot. So these guys are dropping piles by their weight. So that's all they do over there. If you cannot drive the piles in there and you need to get in there, you got the problems with penetration. You can do a pilot hole 4 inch less than diagonal of the square pile or 1 inch less than the diameter of the round pile. Jetting, you can also use jetting to basically get your pile to the design penetration. It's basically a 2.5 inch diameter pipe, 150 psi pressure. You drop a pile minimum of 1 foot below the tip of the elevation or 100 blows per foot. I don't like jetting really, but if you have to do it, I guess you can. In terms of the hammer size, that's kind of important to kind of know what type of hammer to use. If you use a air, hydraulic, diesel, let's say you got a concrete pile, ram weight 3,000 pound minimum. You're gonna have a stroke of 5 feet. The hammer energy 250 R. R is the design load. So if you got a pile that carries, let's say, 40 tons, so it'd be 250 times 40, but not less than, of course, 1 foot-pound per pound of pile weight. So TechSide's got that as a guidelines to come up with hammer size based on the timber pile, steel pile, or concrete pile. Hammer formulas, if you want to know the dynamic capacity of the piles at the time of driving, you can use dynamic hammer formulas. They're not very accurate, but you can use it based on knowing the ram weight, stroke, blow counts. Pile setup or pile freeze. So when you drive a pile, you develop pore pressure around the pile, and your pile capacity is going to be lower in clays. And so that's like called dynamic pile capacity. With time, the pore pressure dissipates. This is time, and you get a strength gain with time. So, for example, in clays, I use a rule of thumb of usually 2. Dynamic capacity is half of the static capacity. So, in other words, you drive a pile in clay, you let it sit, and the capacity doubles. In sand, it doesn't affect it very much. So you drop a pile in sand, the capacity doing the driving is close to what it is afterwards because pore water dissipation is quick. Pile relaxation. Pile can lose its strength after driving in certain soils, such as very dense sands, inorganic silt, stiff fissured clays, and gravels. Pile relaxation has been observed mostly for end-bearing piles. Pile heave. We have a lot of pile heave, of course, like in Houston area, Houston Ship Channel Toll Bridge. I was out there 40 years ago driving the piles for the existing Houston Ship Channel Toll Bridge. We usually steel pipe piles, and you would drive one pile and the other piles would come out. It's called pile heave. We ran pile load tests. There was no strength loss. The capacities were still good. So if you got soils and you put the piles close together, you drive these piles, it pushes the soils around it up, and it's called pile heave. And if you got piles here, it pushes these piles up. Dynamic pile load test. If you could drive a pile, you hit refusal, you cannot go deeper. This is a pre-stressed concrete pile. These piles for a bridge in Conroe. We couldn't drive them in. I guess they had a small hammer or whatever. They couldn't drive them in. Want to know what the capacities are, you can go ahead and do dynamic analysis. Using pile driving monitoring, you can find out the stresses, pile integrity, hammer performance, capacity at the time of testing, which is dynamic capacity. So you go out there and you put strain gauge and accelerometers on both sides of the pile. That's the hammer pile head. Like that. You put the accelerometer and strain gauge. You drive the piles, and you get capacity using the PDA, pile driving analyzer. So we had for abutment 1, shaft resistance was 365 kips. and the tip resistance 129 kips with total of 494 kips. That exceeded what our design values were. So although the piles were shallow, some of them, they meet the capacity requirements at the time of driving. So when the dynamic capacities exceed our static calculations, the piles are good. They could cut the top of them and have a shallower pile. Static load test is a really good, like a Texas quick load test. You put your frame in. There's your jack. You jack against your frame. Your frame is, 2 piles or 2 drill piers. You set it up, those 2 piles or piers are in tension. You push against the frame. These are your dial gauges. You measure the settlement as you load it. Dial gauges, you put it all around. This is your jack. You jack against your frame. So as you load up this stuff, this is your load settlement curve. So you got to kind of get failure here, somewhere about 2,200 kilonewton. TxDOT, for pile design, you can use either double tangent method or plunging failure method. So you get a plunging load divided by 2.3. That's your allowable load. You got a factor of safety. Double tangent method is another method. Plunging failure method, you take the plunging failure divided by 2.3. Here's a pile in a capacity, it's a pile load test. You load up the stuff, you pile, static capacity. This is start plunging in here. You get a point where you get a slope of about 0.5 inch per ton. You draw a slope, and you draw a slope here. This is your ultimate capacity. Use a factor of safety of 2. The factor of safety 2, you got a allowable capacity for this pile of 63.5 tons. So had a K factor of, about 1.5. 42.3 was from a dynamic, pile formula calculation. And of course, this is your static capacity. Here's another one. Drill shaft. You basically do a tangent here, double tangent method, load settlement. Here you come over here, point where gross settlement exceeds 0.01 inch per ton. This is your ultimate capacity, about 740 tons. Your allowable is 370 tons. K factor, as we discussed, is the maximum static load calculated over what you calculate from, hammer formulas. Usually it's about 1.5 or 2. Drill foundations. When you have a lot of the bridges that we do nowadays, they go on drill piers. They don't do drive piles as much. And especially you got the waters, you got to do casing in there. And of course, you drill underneath it. You got to use a slurry method of construction in there because of presence of sands. That's a steel cage. Again, you drill in a pile here, drill piers. It's the auger. That's your steel cage. It's another bridge drilling here. The drill pier, you can see the casing in the water. You case it, in the water, and then you basically stab that casing into the mud line, and you drill underneath it using a slurry method of construction. That's your steel cage. These are drill piers there. You can see the drill piers here. Steel cage. With drill shaft, of course, we use the drill shaft design manual. Uses LRFD, axial capacity, and this is the cumulative friction, and this is unit frictional resistance. And you can see the accumulated friction, the unit frictional resistance, capacity with end bearing and without end bearing. So you got a higher capacity if you count on the end bearing. E&F factors, we talked about for drill piers. Here we disregarded top 5 feet. You go to the skin friction, is a cumulative value, F factor. This is the end bearing, you get sand, it comes up. The same concept, Q is PF plus AE, QT is 0.7 PF. You got drill shaft 24 inches, perimeter 6.28 feet, and area of 3.14 square feet. Your capacity is 24 kips in compression and 12.74 kips for uplift. Same with here. Here's another skin friction, cumulative value for drill shaft. Here's the end bearing. Go through the same procedure and calculate it. Allowable drill shaft service loads for 20-inch shafts is 175 tons. For 120-inch diameter shaft is 4,400 tons, which is a lot. Texas does not use bell piers for bridges. So you don't bell anything. You drill your piers, auger them. Of course, typical, smaller ones, they got auger you drill with, and you got the reamer. You drill hole with the auger. It's a drill truck. You drill. That's the reamer there. For shallow ones, you would use the bell, but not for deep ones. You drill a hole. You can have about up to 3 inches of water in it. You measure the depth. Check with a hand penetrometer. Make sure you got the proper strength at the bottom. You measure the bell. Make sure you have proper bell size. This is a bell tool for shallow piers. You sweep them in. Make sure you got the right size bell. You put the steel cage in. Pour concrete. Make sure it doesn't hit the sides. You can use trimming. It's a lot better. It doesn't let the concrete hit the sides. If you have, this is a dry method of construction, you drill a hole, you put your cage in, you put a trim in, and you put concrete from bottom up. If you got sandy soils, you can use a casing method of construction. You drill your hole, you put your steel cage in, steel casing in. You drill through the casing, and of course, that prevents the soil from caving in. That's the steel casing. You drill through it, get the soil out, check with a hand penetrometer, make sure you got a proper strength soils. You put the reamer in if you need to. You drill and make your bell, you put your steel cage in, pour concrete. You trim it down, pull the casing out. You drill a hole, and you put your steel casing in. You drill below it, trimming the concrete from bottom up. Slurry, that's what the TxDOT uses on a lot of their bridges. Start drilling the hole, use bentonite, usually about 4 to 8% bentonite with water. That's the mud pit. You mix the bentonite in here. You pump it into the hole. You drill your hole. You get to the design depth. It's the straight shaft. You put your steel cage in. The mud kind of pushes against the sand and loose materials. It keeps it in place. Plus, you got hydrostatic pressure. So you get the bentonite cake, and also you get the hydrostatic pressure to keep the hole open. And then you start pumping the concrete with the trimming from bottom up. Concrete unit weight is 150 PCF. Soil is about, I mean, the slurry is about 70. So it's heavier, so it replaces the slurry. You recycle your slurry, use it for the next hole, fill it up with concrete, you got your steel in it. So you're going to start drilling, use the slurry to drill through the sand. You put your steel casing in, then you start put the concrete from bottom up. Auger cast piles. Some of the textile bridges, they use auger cast piles on their projects. This is a big auger. It's got a hole in the middle of it. These are auger cast piles. You drill in there. You pump grout through the middle of it. It's like that. It's got a hole in the middle of it. That's the auger cast pile head, drill head. Right there. You put your steel cage in after you put the grout in. You grout it and then you put the cage in. You push it in there. Some of these auger cast piles got only one 1-inch diameter, steel cage in them. These are for small bridges. Pipe piles, you drop piles in there and you put pipes in it on it to support it. I mean, I've seen big piles. You can use drill piers as well. You see the piles to support the pipe. Here's again using piles to support the pipe. Scour, Geotech's got to provide D50 for scour analysis. That's diameter 50% finer on grain size curve. So you got the grain size curve. This is a D50 diameter that more than 50% of the material passes. In this case, it's a 0.05 millimeter. The 50% of the materials is smaller. So we're going to give you that value of 0.05. D50 should be within top 15 feet for calculations of the channel scour. Here's a project that experienced scour. That's US 59, and Interstate 69 projects. That's San Jacinto River. That's north of Humboldt, Montgomery County. You can see Bent's 1813. You can see the northbound frontage road, northbound main lane, southbound main lanes, southbound frontage road. This is the San Jacinto River going underneath the bridge. In 2017, where we had that big Harvey, the whole bridge got flooded. Here's San Jacinto River going this way. A lot of trash. Water was coming this way. Major scour, kind of washed out a bunch of soil on the columns. You can see bend 13, bend 14, bend 15, bend 16, bend 17, bend 18. This is the topography underneath of San Jacinto River. That's a water flow. You do the sonar, bend 14, there was no scour. You go to bend 16, 25 foot of scour. So these piers could not basically safely support the bridge. Bend 17, you got 25 foot scour. They had to come in, break up the bridge, putting some new drill piers in, deeper to account for the scour. This bridge had all kinds of different foundations throughout the years. So they come in and put in new drill piers in, deeper. They start building the vents, putting a new bridge in with deeper drill piers. Scour types, you got the local steep-sided scour pits around the single pile or pier. Global, where you got or dispersive scour, like a shallow white depression under around individual installations. Overhead seabed movement, erosion, deposition, and bed form movements. So if you got rock, you got hard rock or so, TCP block counts less than 4 inch per 100, they're not susceptible to scour. You got soft shale, blow counts 12 inch per 100 blows, mildly susceptible to scour. Clays, hard clays, 12 inch per 100 blows, mildly susceptible, but not considered over time span of flood events. Soft clays, they're susceptible to moderate scour, and sands all are susceptible to scour. So this is kind of an armor that you put around your bridge, kind of for to reduce potential for scour. Slope stability of the abutments. Again, if you use fat clay for your abutments, it can fail. You need to have good slopes on it, minimum 3-to-1, or if you got sandy soils, 4-to-1. You may not have all that space for it. We had a lot of failures of the abutments. Every time we do a bridge, you got to do a slope stability at the abutment, make sure the slopes are stable. You can see the failure here. Erosion and failures. Abutment failure. A little bit about Houston Ship Channel Bridge. Great bridge. H&TV kind of construction management. Extra is the client. Thanks to them for the pictures. That's State Highway 225 overpass. They used a lot of steel on this thing. And you can see coming in here, the approach, going over Houston Ship Channel. Big columns. Lots of concrete and steel. It's amazing. The drill piers that they used with this bridge were huge. Here's the augering for the drill piers. Look at it. I mean, these are huge drill piers they used. They were like 200 foot deep. Casing, putting into water, of course. A lot of steel cage. See the drill pier group there. That's it. Got some good pictures of the project. Send them to me. This presentation is going to be on YouTube. We're going to have a program evaluation polling. If you can answer it, that'd be good. I can find a poll right here. Tell me what you think. You need to reach me. You can reach me. My email is de@geotecheng.com. My number is 713-699-4000. We're going to have a bunch of webinars. We have your contact information. You're going to be on our list. You're going to get an hour and a half PDH. We had some technical problems. Sorry about that. Questions?